we want to start today by looking at the last 3 sections of chapter 4. And in particular, we're looking at those sections dealing specifically with the atom. So we know, we've discussed this already, that the atom is the smallest particle of a substance that retains all of the characteristics of that substance. What we really haven't gotten into yet is, what does that actually mean? And for that, we're going to need to introduce a couple of extra ideas. And so one of those extra ideas that we're going to introduce is something called the atomic theory. Now, in your textbook, you might hear this referred to as Dalton's atomic theory, so named for John Dalton, the physicist who kind of theorized these ideas first, kind of put them out in writing. So in this theory, we have the idea that atoms are these tiny little particles of matter, and that there are some things that help us to differentiate atoms and molecules, and atoms of one kind of element and atoms of another kind of element. So kind of breaking it down into its most simple of parts. If I'm looking at a sample of sodium, all of the atoms of that sample of sodium are going to look similar to each other. Not necessarily identical. We'll get into how they're not exactly the same in a minute, but they should have some sort of kind of quality to them that allows us to go, that's sodium. And I know it's sodium because I see this. And if I were to take that sodium and compare it to a sample of magnesium, I would be able to see that there is a difference between the two. All of the atoms of the magnesium would look exactly the same as each other, but there'd be a difference between the sodium atoms and the magnesium atoms. And we'll get into what that difference is in just a minute. Now, if multiple elements combine and form compounds, it'll be those atoms that are going to rearrange themselves to make those compounds. And as we talked about in chapter 3, that arrangement is always going to have a very fixed and well-known ratio. Carbon dioxide is always going to have 1 carbon atom and 2 oxygen atoms in it. That's what makes it carbon dioxide. Water is always going to have one oxygen and 2 hydrogens. That's what makes it water. When we have atoms or molecules reacting chemically with each other, this is what becomes the basis of a chemical reaction. This is where we can get new compounds, new substances out of our old substances. But the thing that we have to remember, we have to keep special attention on, is this idea right here. You've probably heard of the law of conservation of matter. Well, this is a retelling of that law of conservation at the atomic level. Atoms cannot be created or destroyed in a chemical reaction. All that happens when we have a chemical reaction is that those atoms rearrange themselves in some kind of way to create new molecules, new compounds. So the atoms themselves don't go away. They get reorganized. Now, inside the atom itself, we have three different sets of particles. We have the protons. The protons have a positive charge. We have the neutrons, which have no charge. They are neutral. And we have the electrons, which have a negative charge. The key things about these subatomic particles we have to keep in mind the idea of this electrostatic electron repulsion and attraction. The neutrons, well, since they're neutral, they really don't participate in that attraction or repulsion. But protons tend to repel each other. They have the same charge. Electrons tend to repel each other. They have the same kind of charge. The thing that largely keeps an atom intact is the fact that even though the electrons are pushing against each other and the protons are pushing against each other, the protons and the electrons are attracting each other. And that attraction between them is one of the primary ways that the atom kind of stays together. There's another component of it, something that we won't get into too deep, but it's called strong nuclear force. Basically, it keeps those protons close enough together to form a nucleus. But again, we won't get too deep into that. That's more of a next week topic when we get into nuclear chemistry and talking about why some things are radioactive and why some things aren't. Strong nuclear force has a lot to do with that. In terms of atomic structure, we can think of the atomic structure as being two things. In the center of that atom, we have the nucleus. The nucleus contains both the protons and the neutrons. What's interesting about the nucleus is that it is the epitome of extreme density. In the atom, the nucleus makes up over 99% of the mass of the entire atom. Yet it takes up less than 1% of the total volume of the atom. The electrons, on the other hand, exist in kind of the opposite space. Electrons are over 99% of the volume of an atom, but less than 1% of the mass. Why that big disparity? Why that large difference? Well, that electron repulsion really does force those electrons to spread out from each other. And so the resulting atom is huge by comparison. And so what we think of is we think of the atom primarily as empty space. Because while the atom does have mass, that mass is largely centered and collected in a very small amount of volume. Whereas most of the atom itself is the electrons, and the electrons have virtually no mass. Just to give you a kind of a size comparison, an electron is about 5,000 times less massive than a proton. And neutrons and protons are about the same. A neutron's slightly heavier, but not enough for us to really care about. So again, put that in perspective, 5,000 times the mass if I'm comparing a proton and a neutron, or a proton and an electron. That means a lot. And so one of the ways we came up with this particular model of the atom is we did some experiments. And one of the experiments that we did, it's called the gold foil experiment. It's highlighted in your textbook. We're not covering it here deeply. But basically, someone shot really heavy particles at this really tiny piece of gold foil. And what happened? Most of the really heavy particles went straight through. Now, that's not what you would have expected to happen. You'd expect, okay, I throw one object at another, it's going to bounce off. But at the particular level, at that atomic level, those heavy particles shot through all of this empty space. Even if they encountered an electron, the mass of those particles was about 20,000 times that of an electron. That'd be like you running at 50 miles an hour and encountering a gnat. Unless that gnat goes into your eye and you can't see, chances are you aren't even going to notice it's there. That was basically what happened. That's how we came up with this kind of model for the atom overall. We're not going to talk much about atomic mass units. When we calculate masses, the numbers here on the periodic table give us the average mass of an atom of whatever element it is that we're interested in. This is how they calculate it. They based it based off of carbon-12 and the mass of carbon-12, and we kind of set that value and kind of created an equation for figuring out every other mass. But you can see here, there's that difference I was talking about. Protons and neutrons practically have the same mass. Compare that to an electron. I believe I misspoke. I said 5,000. It's more like 2,000, but still not enough to care about. This table kind of summarizes all of that, where to find it, what the masses are, what the charges are, some symbols that we can use to kind of abbreviate protons, neutrons, and electrons. But what I want to do for the rest of our time, I want you to break up into groups again. We've got about 40 minutes. And to address this atomic number and mass number piece here, what we're going to do is we're going to work through the activity here. And so just kind of looking at the activity itself, you can see the first page is all information. Most of the second page is information as well. But what you're going to do is you're going to get into the study questions and the exercises here. And you can stop after this table on page 4. You don't need to answer the problems here at the bottom. I mean, you can. It's really not going to do that much. It's basically just kind of asking you to rationalize that difference in size between the nucleus and the electrons. And we kind of already talked about that. So rather than have you try to do some calculations to actually figure it out, we've kind of already scaled that. So go ahead, get into some groups. Again, you know, I don't care really how big the groups are. Try to keep them under 4 or 5 people if you can. Work with whoever you feel comfortable working with. I'm going to bounce around and check in on you as things go by. And if we all get kind of stuck in some place, we'll stop and reset and kind of work through it together. Any questions? All right, go ahead and start.